So let's go ahead and get started with part 2. And when we look at part 2, what we're looking at now is still a little bit more of a review, but now we're going to look at how sound waves can be both a compressional wave or longitudinal wave as well as a transverse wave. So I want you to pay really close attention, okay? You have all these dots right in here. And where we have a lot of dots, we have high pressure, okay? We have high number of particles. And where we have high number of particles, where we have high pressure, notice we have the highest amplitude of our wave. We have the crest of a transverse wave. So when we think about a crest on a transverse wave, that is where you have a large number of particles taking place in a longitudinal wave. Okay? Then I want you to look at this region right here. You don't have a lot of dots in this region. And it is the lowest number of dots that you have, okay? It has the least amount of pressure, and it is the lowest part of your wave, called a trough. So in a longitudinal wave, if I just don't have a lot of dots, I have less pressure, which means I have less density, and thus the whole idea, once again, that I'm looking at, the fact that I have a trough. So this is that idea of comparing a longitudinal wave versus a compressional wave or a transverse wave. And if you notice on your paper, the next thing that you're supposed to be doing is drawing in this box. And so I'm going to show you lots of examples here that you could be using and comparing, okay, a longitudinal wave and a transverse wave. So on this next picture, we have a speaker right here, okay, and this speaker is producing sound that my ear will eventually pick up. So when I look at this, this is basically the idea of, hey, where I have this crest, where I have this crest and this crest is where I have high amount of particles, I have high pressure, I have the highest part of a transverse wave. Okay, this is actually my longitudinal wave moving right here. And so here is where my sound is going to start right here with the speaker as soon as it stops. Okay, here is my compression, and it moves all the way down here to my ear. This is my eardrum, okay? This is the tympanic membrane. And you can see how it pushes on that. And when I get a compression, it pushes. But when I don't get a compression and I have a rarefaction, it pushes back in the other way. That is the idea of a rarefaction. And where I have rarefactions is where I have the lowest amount. It's where I have the least amount of particles. Okay, and that's why my tympanic membrane is actually going to go in reverse. That is extremely important. So this is your longitudinal wave, this is your transverse wave. When we look at another example here, you have a tuning fork, okay? And with a tuning fork, here you go, it is vibrating. I can feel the vibration in my hand, but I can also see it going back and forth, going a little bit further apart, like you see in this picture here, but then getting closer together. So before we ever start, there is no sound right here. And how do I know that there's no sound right here? Because all of these particles are equal distance apart. There is absolutely nothing that I can hear from this tuning fork. But when I hit it on the table, as you can hear, when I hit it on that table, I then start making compressions. Those compressions are going to travel. So here's that same compression moving forward to my eardrum. Right behind it, okay, right behind it, I have this taking place. That tuning fork goes together. If I could do a still motion picture, we could do it far apart, close together, far apart. And where you eventually get that constant vibration back and forth, back and forth, back and forth, sending one compression and another rarefaction right behind the first ones, okay? I have another picture here that was exactly like what we looked at with the guitar a while back. And so when we looked at the guitar, we talked about how there was an increased pressure where I had compressions. Every single compression had increased pressure. Every single area there is a crest where I have increased pressure, where I have high density. And that is our transition into Thursday's class. Where I have a decreased pressure, I have a rarefaction, I have lower particles, lower density, the lowest portion of my transverse wave, Okay, so here's a transverse wave, here's a longitudinal wave. Transverse waves happen with the actual vibration of the tuning fork going back and forth, the vibration of a string. It's a solid object that's moving, and therefore it's a transverse wave. But when it comes to my ear, it comes to my ear in a longitudinal wave. So when you get to this box that it says in the box on your notes, I have shown you 4 or 5 examples here of the differences between transverse waves and longitudinal waves. So by this point, you should have already drawn these. If you haven't, this is exactly what I want in this box right here. It needs to be labeled. You need to have what type of wave it is, longitudinal or transverse. You need to label rarefactions, you need to label compressions, you need to label crests, and you need to label troughs. Make sure you're doing that. Okay, now let's go ahead and talk about these ideas of amplitude versus frequency. So you're just filling in the blanks here, okay? When we talk about intensity of sound, we call this volume, you can call this intensity, you can call this loudness or quietness, but the more technical term is intensity. So it's basically what we hear, how much energy a wave is carrying. So what sounds loud to me may not sound quite as loud to you, might sound really, really loud to somebody else. So the greater the amplitude of a wave, the more energy that it carries. So when I talk about amplitude, remember it's how high a wave is. So that's a really big amplitude compared to this guy who has a small amplitude. In a compressional wave or a longitudinal wave, the amplitude is greater and the particles are squeezed more together, okay? And that makes sense. So where I push all these particles, it basically makes a big hill. It goes up. There's nowhere else for it to go. So where I have a larger amplitude, like you see in this picture right here, I have a much louder sound. It would be like me talking really, 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 really loud. Or if I bounce a ball on the floor, it bounces really high up when I push it down really, really hard. But my ball won't bounce quite so high if I don't smash it down on the floor as hard as I did in the very first instance. So smaller amplitude, me not bouncing the ball as much, gives me a softer sound of that ball bouncing, but it also won't have as big of a rebound. It won't come up as high. Okay, so when we're looking at these two pictures, what you're wanting to do, if I can get it to scroll forward there, I want you to take a colored pencil, preferably yellow, just so that you can see the outline of the transverse wave here inside of that longitudinal wave. And when I'm looking at this very top picture here, okay, I'm going to put a star. Let me put a star with a yellow star. When I look at this very top picture, this is a wave that has a low amplitude. So compared to the wave right below it, it has a really, really high amplitude. And if I pay close attention to the particles underneath the highest part of my wave where I have the highest density, the highest number of particles, there's not as many particles as there is in this one. There are still a lot of particles here, but if you look down here, I can hardly see any little white spaces because there's just so many. So what this means is that in that compressional wave that we have, this is your compression, okay, and this is your crest. What I'm looking at here is in a wave that just doesn't have as high of an amplitude, there's not as much energy, okay? So there's not as much amplitude in the wave. There's just not as many particles, and therefore you just don't have as much sound getting to your ear as much. And so this is really what you need to be writing underneath the picture, because on your notes, what it's asking you to do is to identify the loudness of each one. This is a quiet sound. Oops, sorry. This is a quiet sound right here, and this is the information that you would write for the quiet sound. Not as much energy, lower amplitude, less particles, as you can see in the picture itself. But then when I look at this picture down here with the green star on it, this guy has a lot of amplitude, has a lot of high number of particles, has a higher crest, okay? And when I look at a higher crest, basically what I end up with is saying that, hey, I have a lot of energy here. I'm talking really, really loud and I'm pushing a lot of molecules into your ear right now, and so my volume has increased. I have a lot of energy behind my talking. So if I were to actually record this wave, this is what it would end up looking like, okay? So you need to make sure that you basically have written this information under the wave that has a loud sound and write this information underneath the one that has a quiet sound. Amplitude is extremely important. It is what determines how loud something is. Then the second thing that is important in this lesson is frequency. And frequency determines the pitch, how high or how low that pitch is. So pitch of a sound is determined by how many waves are passing by a given point in a second. And so in this picture right here, I have a wave that is having a high number of waves pass every single second. Therefore, I have a much higher pitch. It would be like you inhaling helium, and we'll talk about that in class. So an object that is actually vibrating faster, like this tuning fork is, for example, is going to have a higher frequency than a tuning fork that wouldn't vibrate quite as quickly. And so that's going to be why it sounds higher than a tuning fork that doesn't quite have so much. Each one of these circles on this loudspeaker is representing the darker circles are representing compressions. So where I have highlighted here, the compressions are going to be these darker blue circles right here. These are your compressions, okay? And notice how many compressions I have coming out of the top speaker. That's because this is where your treble is. This is where your higher pitches are, the higher number of compressions. This is your treble and your higher pitch sounds. But in the bottom picture, you can see that I don't have but one coming out, okay? The same sound is coming out of both. The problem is that these are lower pitch sounds. There's lower number of compressions. Therefore, there's lower frequency, less number of waves. And this is basically where you get the bass, the boom, boom, boom that you hear in vehicles going down the road or as you eat in the commons or something. Okay, so with that being said, we have these two pictures. And with these two pictures, once again, we're going to illustrate, or we're going to write down below the pictures exactly what's taking place. So in this very top picture, we have a high frequency, we have a high number of waves. Once again, I want you to color code, okay, so you can actually see. So I have this high frequency, and as you can see, a high number of particles in this region right here. And where I have those high number of particles in this region, I have a high pitch. So high number of waves means I have a shorter wavelength, as you can see. This is representing your wavelength right there. High frequency, a large number, I actually have 4 waves traveling in this same spot, whereas down below, I only have 2 waves, okay? So my frequency, is going to be 2. And therefore, I am not going to have as high of a sound. My lower pitches are going to be where I have lower frequencies. My higher pitches are going to be where I have a higher frequency. So that sort of makes sense. High number of waves, high amount of frequency, and a high pitched sound. Okay, if I have a low number of waves, I have a low frequency and a low pitched sound. So frequency is extremely important in what determines how high or how low that note is going to be portrayed to your ear. Okay, so here we have, basically I could look at this as like a clarinet. If I could choose a color, you can see a clarinet versus an oboe. And if you don't know what that is, you can just think of a violin versus a really big bass cello. And so once again, something that's smaller is going to produce this more frequent wave that hits my ear, and therefore it's going to be a higher pitched sound. Okay, but with this oboe, or with this really deep, big instrument, I get a longer wavelength, and so I have lower frequencies, and that sound is going to be much, 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 much deeper sounding. Last thing on your notes, how do we measure sound? Well, I can say something's loud or quiet. The true way of doing it is saying how many decibels it has. That's the scientific way, little d, capital B. And so you can see here, typically we shouldn't be listening to anything over 85, though most of the time you guys turn those headphones up after school hours and listen to it very, very, very loud. So what you're going to do with the rest of this, you are going to go to Edpuzzle, and you're going to go watch Brain Pop Sound Part 1. Okay, and you're going to have to, oh, sorry, you've already watched Brain Pop, or you've already done Part 1 and Part 2 for your notes. You're going to go to, you're going to stay in Edpuzzle, and you're going to find PS4.1 Brain Pop on Sound. And no, you have not watched this yet, okay? It is under no due date right here. It's under no due date in Edpuzzle at the very bottom of the list. So make sure that you find that. It is there, I promise. And if you turn your notes over on the back, you will find Part 1 of the homework, or in-class work, hopefully, that you can get done on the back. And this is going to be basically filling in the blanks with these different definitions. So you're going to be watching the Edpuzzle video, Brain Pop Sound. I'm going to be looking that you've completed it, and then you're going to finish Part 1 activity on the back of your notes. Okay? When you get done with that, the part 2 activity on the back of your notes that looks like this right here, okay? When you're going to get to that, that can be done at home. You do not need BrainPop, okay? So make sure that if you don't get any of this completed in class, I'm wondering exactly if you used your time wisely, but it's also going to be due Thursday the next time. So you can come in Wednesday during lunch and get this finished up. You can come in Thursday during lunch, depending on if you haven't seen me by then. That would apply to Mr. Tunnel's class, and get this finished up, but it is due by Thursday. Okay, and then number 4, if you do get finished with all that, there is an activity that you can get from the teacher. It is a sort activity, and the actual bag of materials is in the basket on your desk, and the directions are on the handout that you will get from him or her whenever you turn in your paper to say, hey, I'm done with part 1 and part 2. Have a good day, guys.